The next thing that I want to show you with loops is how you can do element by element operations on vectors with loops. Yes, what you're going to see now, you can completely do it with just one line of code with the element by element operations that you know so well, but it's important to know how these things actually work. So it may still be hard for you and me to justify the introduction of loops with these examples, but hold on and follow me. Now, we will have something like a mini project and we will complete it in the main project lecture for this section. Let's say that we want to calculate and visualize the motion of a point in a two-dimensional space. If you remember from your physics classes, the equation of motion in one dimension is simply, I'm going to copy and paste them, is x of t equals to x0 plus v0 for the x multiplied by the time, then the acceleration multiplied by the time squared divided by 2. This is true for one dimension. Since we're going to work on two dimensions, we will simply have the same equation for the second dimension. We also need initial conditions. x0 and y0 will be zeros for both of the equations, so we won't bother with them at all. We only need velocity, acceleration, angle, and time. So the angle will be pi divided by 4, so 45 degrees. The velocity on the x-axis will be vx will be 10. The velocity on the y-axis will be 20. The acceleration on the y-axis will be minus 9.8. So this will be the deceleration due to gravity. And finally, we want the time. Let's say that we want to observe the motion for the first 5 seconds for each second. So we are going to start from 0 up to 5. So we have the 0th second, the 1st, 2nd, 4th, and 5th second. 6 points. Now let's create our for loop. For I equals to 1 to 6. Since we have only 5 seconds, but we are also including the 0th seconds, we have 6 elements in the t vector, but instead of hard coding it from 1 to 6, we can simply say from 1 to the length of the t, since t is our variable. And inside the loop, we will calculate our x and y values. And here we will use our indexer for both x and t and for y and t. So we are going to say x of I, so we're going to address each individual x point for each individual respective time. Since x0 we don't have it, we are going to simply remove it from here. We don't have any acceleration on the x-axis, so these are the equations that we are left with. Here we will simply have v of x multiplied by the current time. So we are taking the first point from the x-axis and the first second from the time vector. We're going to do the same thing for the y, and we are going to use the second equation now. So vy times t of I plus ay, the acceleration, times t of I squared divided by 2. And we are going to end. And we are going to suppress the output. So what will happen now is for every iteration of our loop, we will get a new x calculated with the corresponding t. Actually, let's not suppress the outputs. Let's run it like that. And as you can see, if we start from the beginning, in the beginning, x and y are equal to 0. They have only one single value. On the next iteration, x has two values, 0 and 10. Y has 0 and 15.1. On the next iteration, we have 3 values. On the next iteration, we have 4 values. And on the next iteration, we have 5 values. And on the last iteration, we have 6 values for both x and y. We can plot these now, so we can say plot x and y. And we get the curve of our motion. We can include this in our file, of course, so we can say plot x and y, so that we can get the results at the end to visualize them. There it is. So we start from here, and this is our motion. As you can see, this is a very rigid graph, very rigid representation, because we have very few points. This graph is a bit ugly, so instead of using a line, let's use a red circle for each of the points, and that will show us each of the points that we have calculated. Now, as you can see, these are the 6 points where our point is in space for the respective time with each of the conditions. Now, let's do something about this. Let's keep it at 5 seconds, but let's change the incrementation. Let's make it have 50 points. So we're going to increment by 0.1. If we run it again, we get a lot more points. So we get more precise motion. We get more precise points of the motion. And since our for loop was directly tied to the length of the t, it automatically adjusted itself for the new length of t, for the new amount of values that it needs to recalculate. Now you can do both of these calculations without the need of a loop, so you can simply say, I'm just going to copy and paste it. So you can simply do this and get rid of the loop. You'll get the exact same result. As you can see here, I'm using element wise powering, and that's pretty much everything that you need to do. You'll get the exact same results. These are only x1 and y1, and we get the exact same results. So what's the point of loops? Well, in the project you will see how to go from this to this, and you will hardly be able to do it without loops. In the next lecture we will make the need for loops even more evident.